Okay, this is your overview of the C1 topic, structure of the atom. This is lessons 4 and 5. Let's start off with looking at a quick timeline of the model of the atom and how it's changed from the ancient Greeks, who thought that atoms were these tiny little particles, and they kind of weren't wrong in a way. But as science and technology has evolved over time, the ideas have developed with them. It got to about the 1800s, and John Dalton coined the phrase atomos to describe that these were tiny spheres that were made of no other parts. They were just solid little balls, little spheres. That's what he thought atoms were. Nothing inside them, or no other parts to them at least. So they used the word atomos, which means indivisible, hence the word atoms. Then a little bit later, into the 1800s, we've got Thomson, who then did some further work and discovered that actually atoms do have parts. They've got some positive parts and got some negative parts, and the positive part is spread out throughout the whole thing. The negative parts were embedded in very little pockets, little places inside the actual atom. He tried to describe what this was like to people, and he used the phrase the plum pudding model. And again, it's a model because he didn't have an actual sort of picture of what this was like. And the reason it's called plum pudding is that if you were to look at a plum pudding in those days, you could find that your individual plums were sticking out of your pudding, and all of the plum sauce in your pudding as well would have been all of the positive stuff left behind. So hence the phrase plum pudding. Later on, some further experiments were done by Rutherford and Marsden, and these were called alpha scattering, and I'll come on to that a little bit later. But their development changed the model of the atoms, so the positive stuff now wasn't spread out evenly, it was centralized into what we call the nucleus. So the positive stuff is now in the middle, and hence we've got the phrase the nuclear model. All of the negative stuff, again from being spread out, actually has now got a pretty specific area around the edge where it stays. So now we've gone from having a sphere to parts, and now the parts are in very specific places. Niels Bohr came along a little bit later and looked at these electrons, and he found that actually these electrons aren't just in sort of one specific place, they've got very specific places to be, and these are called the shells, or they're called the energy levels. So that was his contribution to the model. And then finally Chadwick came along and looked at the nucleus in more detail and realized that actually not only do we have positive protons here in red, we've actually got some other parts which are called the neutrons, and they've got no charge whatsoever. And we kind of get a picture of what an atom looks like in sort of a modern textbook or revision guide. Let's have a little bit more of a look now at this alpha scattering experiment, because this was a real turning point in the model of the atom. We've gone from parts to very specific parts in specific places. So what did they do? So we'll get this in the right place. Here we go. Alpha scattering experiment. So what they did is they took something called an alpha particle. And now an alpha particle is basically 2 protons and 2 neutrons. There's no electrons here whatsoever. And it's a positive particle, because remember the neutrons have no charge and the protons are positive. They took a thin piece of gold, and it was only a few atoms thick, this piece of gold, very, very thin. And they fired lots and lots and lots of these alpha particles into this piece of gold. And what they expected to see is that if the plum pudding model was true, then all of the pieces should have just passed straight through the piece of gold with no interruptions or no problems. They'd have gone through unscathed. And that worked, they did pass through, but they didn't go in straight lines. What he found is that actually the gold, or something within the gold, was causing these particles to deflect. They were getting scattered all over the place, and some of them even went back the other way. So his question was why? Well, why did that happen? He realised, after doing some careful thinking, that in fact most of the atom is empty space. And the reason that they change direction, some of these alpha particles, is because when they get close to a positive nucleus, they're repelled and pushed in a different direction. Or if they get close to the electrons, they're attracted and change direction as well. And we've got this massive spread of these particles. This atom was interfering with the direction that they were travelling in. Quite a lot of them passed through because they just got through the gaps in between the nucleus and the electrons. So a lot of the stuff did pass through. Sometimes though, an alpha particle would hit the nucleus bang in the centre, and if that happened, it would just bounce back again. And that's what was happening here with some of these. So his conclusion changed the plum pudding model from being all the stuff spread out to all the positive stuff in the middle and all the negative stuff to the outside, with big spaces in between the nuclear model. So that was the alpha scattering experiment. Moving on then, we now look at the modern day version of the atom, which is just over here. And now in a modern textbook you'll see that we've got the nucleus, and in this case I've drawn 7 parts in my nucleus. So I've got 3 protons and I've got 4 neutrons, and you can have different numbers of each. I've also got 3 electrons as well. My protons are positive, my neutrons are neutral, and they're found in the nucleus, and they both have a mass of about 1, so they're similar in size to each other. The electrons, these are found in a shell or an energy level, and these have a negative charge and are very, very small compared to the protons and the neutrons. In fact, you need 1,000 electrons, probably more than that, to be equivalent to 1 proton or 1 neutron. So they're really, really small. This one's called a valence electron, not because it's on its own, but because it's in the outer shell. So if I've got 5 in here, I'd have 5 valence electrons. I've only got 1 in this example. So the valence electron's in the outer shell. When drawing electrons, we always start from the inside, fill that shell up, and then add the rest in the next shell. And if you fill that one up, you then draw another one as well. So we always draw them from inside to outside. So just be mindful of that if you have to draw any atoms. Let's look at some of the main features, and we're nearly done. Atoms are neutral overall, which basically means they've got the same number of protons and they've got the same number of electrons, because protons are positive and electrons are negative. So if you look at my diagram again, look, I've got 3 positives, I've got 3 negatives, plus 3 and minus 3, well, that equals 0, so the overall charge is neutral. The mass, well, this is all in the nucleus. This is made of the protons and the neutrons. Remember, the electrons are too small, they're tiny, aren't they, compared to everything else. And the electrons fill from the inside to the outside, and we can fit 2 in the first shell, 8 in the second shell, and then 8 in the third one. You don't need to worry about the 4th and the 5th one. Atoms are tiny, really, really small. In fact, they're 0.1 of a nanometer, which is 0.1 of a billionth of a meter. Now that's quite a small number to get your heads around, but just accept that they're really tiny. And in fact, if that's the size of the atom, imagine how small the nucleus is. Nucleus is really small. The reason why this is called a model, by the way, is because this just represents what an atom really looks like. If I was to try and draw this to scale, these electrons would be, I'd have to have a piece of paper about 1/2 kilometer big to be able to draw where these electrons should be. The electrons are really far away from the nucleus. So this is not to scale, they don't represent the right sizes. Again, this is why we call this a model of the atom. Alright, it just represents what really goes on. And then finally, I was just going to show you how to calculate the number of neutrons. So if you do have to draw some atoms, it's quite an easy process. If you look on the periodic table, if I had to draw fluorine, and I want to know, right, how do I draw the nucleus? Well, I know that 9 of the parts are protons, and there should be 19 in total. So if I work out 19 minus 9, then that means I've got 10 neutrons left over. And that's how you work out how many neutrons to do. I've done fluorine, and it works for all of the other atoms as well. And there we go. So that's your C1, structure of the atom. That's your overview, and that should be enough to get you going with lessons 4 and 5 now. And we're done.